Hello everyone, in this video we'll be solving problem 215, kth largest element in an array. The problem statement is, we are given an integer array nums and an integer k. We need to return the kth largest element in the array. Please note that it is the kth largest element in the sorted order and not the kth distinct element. And as a follow-up, we need to try to solve this problem without sorting the input array. In example number 1, with this as our input and k given as 2, the kth largest element in the array is 5, which is our output. Similarly, in example number 2, where k is equals to 4, the top fourth element in the array is number 4. Please note that it does not matter if we have the same number appearing twice in the array. Both numbers should be considered as different numbers. I hope you were able to understand the problem statement. The simplest way to solve this problem, if we ignore this requirement of sorting, is to first sort the input array into ascending or descending order and accordingly look for the kth position. With that solution, our time complexity will be O of n log n as we are sorting the array. As this approach needs a sorting and the problem statement is asking us to try to solve without having to sort, let's try a different approach. Another way to solve this problem is by using a quick select algorithm. Quick select algorithm is very similar to quick sort algorithm with a small variation. Quick select algorithm is best suited for scenarios where we are looking for the kth largest element or kth smallest element in an unsorted array. We'll try to use this algorithm to solve the problem. Before we start discussing how quick select works, we first need to understand how quick sort algorithm works. So let's discuss that first. In quicksort algorithm, there are two terminologies that we'll be using, pivot and partition. Pivot is any arbitrary number that we will be selecting in the array, and partition will be the number which will help us divide the array into halves. All of the values to the left hand side of the partition will be less than the partition value, and all of the values on the right hand side will be greater. We'll also be using a divide and conquer technique to break down the problem into smaller halves and solve it separately. To begin with, our pivot will be the last element in the input array, which is 2, and the partition will be the first element. As discussed earlier, all of the elements to the left side of the partition should be less than the current value, and the right hand side should be greater. As there are no elements to the left side of number 3, at least the first condition is sufficed. We start off by checking if nums of I, that is the partition, is it greater than or equal to the nums of pivot. As the condition here is not satisfied, we don't need to do any swap, and then we'll increment our pointer. We leave the partition pointing at 3 and start a while loop between I and p to compare all of the values. Let's call the pointer as j. Now we'll compare the value that j is pointing with the value that the pivot is pointing. As 1 is smaller than 2, we need to move it to the left hand side so that the values on the left of the partition are smaller. So here we'll swap the numbers 3 and 1. Please understand that the reason we are doing this swap is to make sure that all of the elements to the left hand side are smaller than the pivot index. The pivot index value is going to be the key here to determine what values should be on the left while what values should be on the right. After the swap, we'll increment our j pointer to point at 4. We'll do the same comparison again. This time, because 4 is greater than 2, no swap is needed. After the while loop is complete, we'll swap the positions of I and pivot. So 2 will take 3 spot and vice versa. Now if you look at the values on the left hand side of number 2, all are smaller than 2, and on the right hand side all values are greater than 2. It may not be necessarily in the sorted order, but at least the values are smaller. Next step is to tackle the sub-arrays on the left and the right side of the partition separately. On the left hand side, we have an array of size 1. As it only contains one element, there isn't any kind of sorting needed on it, so we'll just ignore it and focus on the right hand side. On the right hand side, we have 4 and 3 in the sub-array. Now we'll apply the same logic here with pivot as 3 and the index or partition will be 4. After applying the same operation, the numbers 3 and 4 will be swapped in the ascending order. Post that, we'll go one level deeper and try to break it down into smaller halves and solve it separately. As there is going to be only one element in each of the subarrays, there isn't any processing that is required. So we'll just move up and try to concatenate or combine all of the outputs. Actually, we are doing an in-place operation here, so we don't need to combine the output of each subarray. Once we have processed all of the nodes, the output will be in the sorted order. The average time complexity of this approach is O of n, where n is the number of elements in the input array. As at each partition, we are reducing the amount of calculations that we need to do. But in a worst case scenario, the time complexity could be O of n square, as we may need to go one level deep whenever we are creating a partition and then comparing its value with the pivot. So if the input array is highly unbalanced, the time complexity could be as worst as n square, and the space complexity is O of 1. As we are not using any recursive start, we are using a while loop to determine the values of the pivot and the partition while maintaining our focus on the smaller subarrays to solve or sort the order. I hope you were able to understand how quick sort algorithm works. Now let's discuss how this will be helpful in implementing the quick select algorithm to solve the problem. As we are looking for the kth element in the input array, if the array was sorted, we know which index we should expect the output to be. For example, let's set k to 3. In the sorted version, the third largest element in the sorted array would be at index 1. If I already know which index to expect the output to be at, I can focus on processing those subarrays that will be closer or overlapping with the position where I'm expecting the output to be. I do not need the elements on the right hand side of the array to be sorted. As long as the elements on the right hand side are greater than the position I'm expecting the output should be, it is good enough to solve the problem. The same reasoning applies to the elements on the left hand side. I don't need it to be sorted. All I need to do is make sure that the elements on the left hand side of the index are less than the current value. So during the loop, we need to make sure that we are adjusting the limits of our subarray so that we can cover the position where we are expecting the output to be. I hope the explanation was helpful in understanding what is the difference between quicksort and quickselect and how it can be used to solve the problem. Let me show you how we can implement this solution using Python. Here's the solution in Python. I've created a separate method quickselect that will help us run the quickselect algorithm. In the quickselect method, I'm first selecting the pivot, which is a random number amongst the elements in the array. After that, I'm initializing three arrays, left, mid, and right. Based on the comparison with the pivot, the numbers in the original array will be saved in appropriate arrays. Next step is to run a for loop and compare the value with the pivot and accordingly add the value in appropriate arrays. After the for loop, I'm comparing the k smallest to check if it is smaller than the length of the left array. It means that the k smallest number should be in the left array, so we call the quickselect method recursively passing the appropriate inputs. If k smallest is less than length of left plus length of mid, it means the pivot is the kth largest element, so we can simply return the pivot as our output. Else we focus on the elements on the right side of the pivot, so we call the quickselect method passing the right array as the input. This code when submitted on LeetCode beats 98% of the submissions in terms of runtime and 15% in terms of memory. Thank you for watching this video. I hope you were able to understand the explanation. The details to access the source code is available in the description below. Feel free to check that out and I will see you in the next one. Thank you.